Thank you very much for the invitation. Yeah, regarding Thomas Strom, I just realized it's now the third person about in my age group who has died recently. There was Eric Palmgren, there was Martin Hoffmann, and now Thomas Strom. So, but I strongly believe he is now in a very good place. And yeah. So what I wanted to, and there's not much more somehow I'm able to say. What I wanted to talk about is how to formalize the extended predicative Mahlo universe, which is something I've been working with Reinhard for quite some time, and how to formulate it in the context of Martin-Löf type theory, which essentially means how to translate explicit mathematics into Martin-Löf type theory. So what I will talk about first is I will introduce Mahlo universe, talk about a little bit about explicit mathematics, then introduce the extended predicative Mahlo universe in explicit mathematics, and then show how to do this in the context of type theory. And then comes a conclusion. So universe in type theory. I started to add some because I was interested in using Martin-Löf type theory as a substitute for Hilbert's finitary methods in a program about the consistency of mathematics. So to take so we have proof theoretic analysis of considerably strong mathematical theories, but I think always once one has an order notation system, one needs to do a second step, namely find some theory in which one can put, or fields one can put one's trust. And that's of course a bit subjective. So everybody has different opinions about it. There are lots of different notions, for instance, about predicativity, but one needs to find a theory in which one can then show that this corresponding order notation system is well founded. Or of course one can try to directly prove the consistency without going via ordinal analysis, but the step via ordinal analysis seems to work, seems to be quite a good approach. And they correspond to large cardinals in set theory, but since we are in a constructive framework, it's more the recursive analog. So that's admissible in cryptoplastic set theory and can be used to reach higher proof theoretic strengths. And they are actually quite important. So in the theorem ACTA, which is based on type theory, they have now natively, so you always could add big universes to ACTA, but just for people using it, they have used really now as a native construct omega many set levels, and then they arrived that suddenly you need another level, you need set omega itself, and discussion is going on that they actually need very well. So this is not just some theoretical study, it has quite practical applications. So Martin-Löf already introduced the hierarchy of universes. So we have several universes which are cumulative and where each element is represented in the next one. And then Eric Palmgren introduced the superuniverse operator, where you define for each family of types a universe closed under those types. So here somehow a little bit of the very tiny, it's actually a small fragment of what you can do with this super universe. So actually it should not be called M, it should be called V, because it's a, or SU for the super universe. So first of all, it means, so for any families of sets, you can form a universe. So you start with the empty family. So you get a smallest universe, and then you can form a universe which is above it, and then you can form the next universe above it, and so on. And then you can, and it's not only that you put one universe above, you can as well put a whole family of universes above. So the very first step you get is, once you have all these finitely many steps, you can take a universe containing all these UNs together. And you go, of course, much, much bigger. Now, so this can be now continued, this approach. So you can now say, let's take a universe and form a universe, form a super universe operator, which takes us families of sets and forms a super universe above it. And then take as a super 2 to the universe, which is closed under the super universe operator. And then you can do the super 3 universe, etc. And you go end levels and alpha levels, etc. And you can go very big. There's a still yet not fully explored notion of very higher order universes, formed by just iterating this hugely. And I think it's from Eric Pumpkin, but I've just forgotten. Now the Mahlo universe now is now a universe where, so in some sense what we always did is we took a universe and formed, we took a universe operator, formed the universe above it, and formed the next universe operator. Now the Mahlo universe is now a universe which is not closed under one operator, which is closed under any operator. So whenever you have a function from families in the Mahlo universe to itself, then there exists a universe closed under it, represented in this universe. So if you have the Mahlo universe, you have a function from families of sets to families of sets. Then you form a subuniverse. You can form a subuniverse closed under it, but that in itself doesn't make it any strong, give it much strength. But adding then an element for it gives you the strength. Now, the problem of the Mahlo universe is that it forms these subuniverses for any total function from the universe in itself. So it refers to the totality. One can still justify it because one can say whenever we get more knowledge about closure of M under F, then we can add it. So and we are exploring some kind of uniform operators. We are not just forming arbitrary functions, but although this is quite a nice idea, I don't know of anybody who has succeeded in really fully formalizing it. So one approach is to, and that's the approach I've taken with Reinhard Kahle, to look at the fact that in order to form UF, you don't need that F is a total function on all of M. All you need is that F is a function from UF to itself. However, that is somehow circular because F is a function from UF, but you are forming F. So that makes it quite difficult to deal with. How do you formalize this in type theory? However, with Reinhardt, we then made the step to go to Pfefferman's explicit mathematics and say now F should just be a term. And we just take now an arbitrary term, form some kind of UF, and then check whether UF is closed under it. And Pfefferman's explicit mathematics is good for it because there you have access to the collection of all terms in a language. So Gerd Jäger already introduced explicit mathematics, but maybe I'll talk a little bit more. So it's introduced, as Gerhard said, to formalize constructive mathematics. It was originally intuitionistic, but then classical logic was added. But if you want really to use it as a constructive framework, you would need to go for the intuitionistic version. So it is presented as a second order language, but that is really, I would say it's more like a technical trick. One could somehow formulate it without referring to it. It just makes the presentation a little bit shorter, which is somehow a hindrance for using it as a foundational framework, as we can use Martin-Löf type theory. Because there's always this feeling, oh, there's some impredicativity coming in, which actually doesn't come at all. It's pretty innocent usage. So in explicit mathematics, we have a notion R of XU, for X is a name for the set U, where U is a set of terms. So everything, we have terms and we have sets of terms. And R of S, S is a name if there is an X which is for it in this relation, and then we have an element. S is an element of T if T is a name, and for the X we have S is an element of it, etc. So. And then you can say what is now a universe. I've written it here a little bit theoretically. That needs, of course, to be translated into the language of explicit mathematics. But it essentially means we have a universe operator. If we have a collection of sets of name, if you have a name, if you have a name such that elements of it are names, then we can form this universe, the set of universe constructors from it. Here I'm using the intuitionistic version, a closure version, which was worked out by Sergei Topailo. So we have the standard basic sets are elements in it, and then it's closed under conjunction, disjunction, implication for all exist, and the join, which is for those from Martin-Löf type theory, that's a sigma type essentially. Now in explicit mathematics, when you can form now the Mahlo universe, which was done by Gerd Jäger. I'm not sure whether Thomas Strahm was involved or not, or whether anybody else was involved. I didn't look up any details here. First of all, because of join, because of the closure of join and some coding, you can replace functions f from families of m to families of m by functions from m to m, because simply you can take an m and form a family out of it and backwards. And and the other thing is that I always had in my Mahlo universe only functions from the universe in itself, but when you come from the super universe operator, it feels quite natural to put as well a family in normal in multi-level type theory, you would add a families of sets to it. In explicit mathematics, you only need one element because of this encoding. So the Mahlo universe in explicit mathematics is not only closed under a function, but has as well an element added to it. Yeah, and then there are external and internal Mahlo universes. External Mahlo universe it exists as well in multi-level type theory. So the external Mahlo universe says that's a set of types, or which is called Z usually, has a Mahlo property, and internal Mahlo universe says we have a universe which has a Mahlo universe which is a type. And the original formulation of axiomatic Mahlo in explicit mathematics was an external one. They are as well called sometimes a red and a green in when discussions with type theorists, because some type theorists say the green Mahlo universe is innocent, whereas a red one, they say, is a bit more problematic. Now, Sergei formulated as well the internal Mahlo universe. Here it's somehow the version which is closed under inductive generation, which just says it's a universe. So the Mahlo universe is a Mahlo universe closed under induction generation, such that for any A in M and any function from M to M, we have that UAF is a universe which contains F and is closed under F and is an element of M. Okay. So now extended predicative Mahlo universes. So so the problem is that, or the problem of the Mahlo universe is always the fact that we say this universe is closed under total functions from M to M, so which really violates the principle of predicativity, that in order to define a set inductively, it needs to be closed. Or when defining a set, you should not refer to the totality you're referring to, but that's what we're doing now. But as I said before, we don't need that F is total on M, so we can instead we can form we say all we need that F is total on itself on URF, but that is somehow a little bit circular. However, what we can do is we can form what we call pre-universes. So we can form a pre-universe AF of the Mahlo universe, where we just try to form the largest universe, a sub-universe of M, closed containing M and closed under F. And in order to get a nice, and actually, in order just to form the Mahlo universe itself, this the PUAF is all we need. And when we later go to the version in type theory, that there we only need, so we will see that we actually I formulate initially just PUAF parallel with M inductively. But in order to express somehow these closure properties, so that the pre-universe is somehow that it's closed under itself, and that we have in order to get an induction principle, we formulate as well PUAFV for any universe V as a universe, largest sub-universe of V closed under A and F. So we define first the set of potential elements of once we have U, we form the potential elements of U relative to the closure operator of A and F. So what are the potential elements? These are the elements we get by using the universe operator. We take A as well, and we try to apply Y, F to any Y and add them to these potential elements. Now, the closure property of the pre-universe is that for all, so U is a potential, the closure property is, noticing I'm thinking too much in terms of type theory at the moment, not so much in terms of explicit mathematics. That's why I'm a bit stumbling here. Every potential element I can form, so U is a universe closed, is a full pre-universe we can form if whenever we have an X, we can form from it as a potential element. And if it's already in V, then it's in U. And now the property of the pre-universe are that of the PU is that it is closed and it is the it's minimal. So if we have any other property which has this closure property, then PU is a subset of it. So it's the smallest set closed under this closure operator. So here's just the picture. We have here the V, which we consider since, so the idea is that we apply it later to the Mahlo universe, that this is somehow part of the Mahlo universe we have constructed. And inside this Mahlo universe, we start to construct the pre-universe of it by adding the element A in it, provided it is in V, by applying F to it, and as well applying any universe operators to it. Where the universe operators are, the really challenging thing here is the join here, because there we not only put one, but we put a real families of sets and join them together. And we add them. Now, if an element is somehow outside the V which we have constructed up to now, then it will not be added, but potentially, if you think of the Mahlo universe, it could be that at a later stage it will be added. Now, a subuniverse, so thinking about a potential V, which is not, we don't know if V is a Mahlo universe, and this is not really finished. We haven't finished constructing it yet. We cannot add PUAFV to it because we don't know whether when V comes bigger, suddenly an element becomes possible to add as well. However, we can add an element to the Mahlo universe once it is independent. And maybe it's easier to look at the picture. So assume we have the V is which candidate would be our Mahlo universe, and assume we form our PUAFU, and assume now this is independent, where independent means that whatever construct from this Mahlo universe stays from this PUAV is already in PUAV. So there is no element, so the function, whenever I apply the function to an element in it, it stays within. Although we don't demand that V is closed under F, we only demand that this POAV is in. And this we call now independent. So AFUV is independent, U is independent of V when any potential element we can form from it is already in V, which means the condition we had before for adding it, which was in this closure operator, here we had always this condition that X is in V. That condition is already fulfilled. So in some sense, then we have that every potential element is in U. So once we have an element which is independent, once it is this PUAFM is independent of M, then we can add a representative to it. So once M is independent, PUAFM is independent of M, then we can add now the axiom which says if it's independent, then UAF is a name and it is an element of M, and UAF is equal to PUAFM. So this is some of the almost the same picture we had before. So except now here this one is M. It could be, one could almost draw here a tilde because this can grow later in, and actually maybe this element which we have been added here, not here, but picture can be improved a bit. So, but what we have is we have this universe M, which is somehow unfinished yet. We form the PUAFM. If the PUAFM is independent of M, then we add an element. Then it will not change when we add later elements to it. So we can, and now we add UAF to it, which means that by adding UAF to the Mahlo universe, we are not destroying some of the reason for adding it, because we never said anything about what happens with this UAF, because the UAF is not inside this smaller triangle we have here. Yeah, and then one can see that the extended predicative Mahlo, the axiomatic Mahlo universe is part of the, fulfills. So the extended predicative Mahlo universe is an axiomatic Mahlo universe. Okay. So before I said that predicative Mahlo universe cannot be cannot be formalized in type theory, because in type theory we don't have access to it. But what we can do is we can formalize explicit mathematics in type theory, and then we can formalize as well the extended predicative Mahlo universe in type theory. So in the following, I will show you a lot of code written in the theorem prover ACTA, which is somehow an implementation of Martin-Löf type theory. Now, so the ultimate goal would be to actually form a closed formalization of the whole thing and then analyze it proof theoretically. However, and whatever rules whatever code I show in the following should be seen as that if we wanted to formulate such a closed formalization, we would need to write this just as standard rules of type theory. So the first thing is to form the set of terms corresponding to the terms in explicit mathematics. One could, if one thinks about this a closed closed type theory we want to do, one could consider not defining them natively as an inductive data type, but just define them as a subset of the a primitive recursive subset of the natural numbers, and also operations as primitive recursive functions. But that's just that's typically when you use a theorem prover, you soon realize that sticking to restricted to operators, close to recursion operators, etc., makes your life quite miserable, and soon you just add things for convenience. And similarly, you just define the terms directly. So here's my definition, or this is a little bit incomplete. I've added code. By the way, all this ACTA code is actually taken directly from ACTA. I wrote a paper with Andreas Abel and Brigitte Pienka, and at one point Andreas said, we haven't written the paper, we have programmed the paper. So this is all type checked. I will indicate when I'm really cheating here. But it's not a complete code, so I've left out lots of things here. So if we look at the set, so we formed a set of terms, which is formed from a combinator. So we just say a term is a combinator applied to a list of terms, and then there's a simultaneous definition of a list of terms. And then we define a reduction operator from terms from terms, which tells you either this term is already in normal form, and for convenience, I add the term itself because that works nicer in this context, or it's reduced to another term. And that works out quite nicely. So you hear this is the K operator, K combinator, and this is the S combinator. Here we have primitive recursion. And this is not necessary for getting explicit mathematics, but I was too lazy to define plus from combinators directly, so I just added it by hand. And then we have, and then we define a reduction that T reduces to S reduces to T in normal form as an operation, which requires proofs because yeah, it's semi-decidable. So it's essentially you just the proofs are just like here I have the example of 1 + 1 is reduces to 2, which goes in 2 steps. So the proof of it here is step to step to step plus it's in normal form. And then what's remarkable is how easy this was. You could prove that the normal forms are unique. And now we define the set of, we need to define the set of names and its elements simultaneously. So it's an inductive recursive definition here. So the set of names. And now you get an interesting thing here. What's going on is you have proofs and you have terms. And the terms should be considered as realizers, and the proofs are proofs that this is actually a realizer. And this is something which I always would like to do as well in, I think in type theory, we should at some point move to something like this as well, rather than coding everything, the proof object and the realizer into one object, to separate them, to have on one hand the proof object and one hand the realizer. So we have now a proof that nut is a name, a proof that ID is a name, etc. And you see here the word NF. because now, there is, of course, a little caveat. I said we define the set of names inductive recursively, but now if I define it, I could easily define it so that for different proofs, I get a different extension. So the set of elements is, so I could have two different proof objects for the same name. And they could then be, the elements could then be different because the set of elements will depend on the proof object. And in order to guarantee uniqueness, I first define the set of names in normal form. And then it's easy to show, and then I define later the set of names not in normal form. And then it's easy to show that if I have two names, two different proofs for a name, then the extensions are the same. So we have a proof that nat is a name, and ID is a name, and the empty set is a name. It's closed under and, or, etc. And here's a closure under join, which remarkably caused really quite big problems, which of course it's not remarkable if you are a little bit more experienced in explicit mathematics. It's obvious. And we have closure under inductive generation here. And simultaneously, so now we define the elements, and this is defined now recursively. And you see here, I have, and it is actually the case that this operation only, so seemingly only depends on the proof of that something is a name, not the elements. The actual element is actually a hidden argument here. However, one can show that if I have two different proofs, we get the same elements. Yeah, and and for the natural numbers, I defined the elements as a separate set. And now
Tony,
here we.
Sorry, Tony, could you have a look on the time? I mean, we are essentially running out of time. You were starting a little bit late, but if you want to discuss your talk, maybe you could try to speed up, not only a little bit. Thanks.
Okay, yeah. Yeah, I'm just thinking about this guy, this fast speaker I recently saw. He could tell my talk in 2 minutes. No. So natural numbers. So we define the set of natural numbers. What are the set of elements? And now you see here that we have realizers. So the set of natural numbers in normal form, we have 0 and successor. But then we have a 0 proof that 0 is an element, and we have the successor proofs that if T is a T, then it sucks T. And then we have the closure under reductions here, which we could do here independently. If we wanted to do inductive generation, then this needs to be defined in one go. Yeah. And then we define the names, general names. If S reduces to T and T is a name in normal form, then S is a name, and the elements are the elements of the reduct. And then we form now the Mahlo universe. And first of all, we form a Mahlo just as a universe, and see now the first complications come soon. So we just have proof that it's closed under all the universe operations. And we can recursively embed the Mahlo universe into, we show that every element of the Mahlo universe is a name. It's not the Mahlo universe yet, it's just a universe at the moment. And extend it to non-normal terms. Now we want to form at least that Mahlo universe is now a universe in itself. So we add a name Mahlo to our name, and the elements are the elements of M, and then immediately actor goes on strike, and actually the problem is the join. And what is the problem with the join is that here we say now, if we have an element of the Mahlo universe, we are defining the join, and we need that if we have an element, if we have an element of the Mahlo universe, and for every element in it, we have an element to it, and here we need to move this element of the universe from the Mahlo universe to a name, and then expand it. And here righteously actor complains, because that's no longer strictly positive, because it could be that there's no guarantee per se that we would not map this to the name Mahlo, and then we would say for every element in M, we get an element of your Mahlo universe. Now the Mahlo universe refers to its full identity itself. So now there are two ways around it. One is to analyze the situation and see that when we add the Mahlo universe, so that we could form the universe and the net set of names simultaneously without having added this Mahlo, and this definition works. And if we now add the Mahlo, the name for Mahlo to the universe, then we just then this will not affect the M. So this is somehow similar to the fact we had before for this recursive independent subuniverses. Once we have formed the M, it will not change anymore, no matter what we add to the bigger universe. The other solution, and that's what Martin Löw took, is to take inductive subuniverses, where you say now you define for every element of the Mahlo universe its extension, and then you add for each element of the Mahlo universe a name to R. However, that means that now we have two different proofs. For instance, that for natural numbers, we have to prove the set of natural numbers. It has two proofs that it's a name, namely the native name and the name which comes from the Mahlo universe. However, still you can do the uniqueness. Yeah.
Yeah. Can you try to finish soon?
Yeah.
Yes.
I'm just
okay.
But that just was somehow. No. So now we can form the preuniverses, and they are formed just inductively by just adding natural numbers and closure and join, etc., where we always just check that here is a crucial thing, and which here it's now the PU referring to M itself. So if the element we construct is already in the Mahlo universe, then we add it to PU and F, and then PU and PU becomes a name. PU is always a name because we can form it possibly after M has been finished, but it's an element of the U if this subuniverse is closed under it. And then we can form as well as operations. So conclusion. So what we have seen here now is that the extended predicative Mahlo universe gives you a more predicative justification of the Mahlo universe. We get induction over it. And there is a formalization in type theory, which is possible. But what needs still to be done is to give carry out this proof static analysis. The upper bound should not be very difficult. So the hard work is then to carry out a well-ordering proof, and doing it in a theorem prover would really be hard work, but that would really gives us full confidence. Doing it on paper, one always, if one does in type theory proofs on paper, there's always, well, it's easy to overlook something. So, yeah. Okay, that's all what I have to say.